No.
Good afternoon. It is time to begin the afternoon session
Good
of
luck. Do us
attending
proud.
junior students Antonio Sanchez through Cody Zapata. You should make your way to the media center at this time. Junior students Antonio Sanchez through Cody Zapata. And any other students that missed their scheduled day and time for testing prior to the session should also report to the media center. Good afternoon.
All right, let's take a look at sample 2, please. Sample 2. Yes?
Oh, I'm gonna go because I wasn't here yesterday.
Oh, so you didn't do
I
it
didn't
yesterday?
get to take it yesterday.
Okay, all right, you better go then. All right. So let's talk about the multiple choice on sample 2. Now, you may have,
Wait, did he see the? Yeah, he's not.
He is. All right, so, so many of you come in, ask questions, looked at the answer books about various things, checked answers. Have we read through the multiple choice ones on this one? The answers? Okay, with that, do you want to do that? Would that be helpful? Okay, so we'll read through the answers on the multiple choice ones, and then we should talk about some of them, because you may have gotten some of those questions answered, you may have figured out some, you may have talked to somebody else, and they kind of explained it to you, maybe that made sense, but there are often in these problems other things going on that you may not have thought about. You may still have gotten the right answer, and that's all well and good, and on the midterm that'd be great, but we're trying to prepare for that, and so any little things I think that we can review and talk about and that you might not have thought of in those problems I think are helpful to do. Matter of fact, that's the whole point of doing these reviews, is to get the chance to go over and talk about those things and so forth. So I would like to do that here if you've got some that you would like to see. So anything from 1 through 45 on sample 2 is fair game. Let's read. How about we read the answers? That would probably be a good start. Okay, so let's do that first. So, what was the first one? Number 2? What do you got? E. Number 3? B. 4? I'm sorry, I don't know which one. 4 was one? C. Yes, it is. 5? D. 7, C, 8, A, I can kind of tell which one, 9 is E, 10, B, 11 we said we could skip till probably first part of next week, 13, C, 15, A, 17, D, 20, B for 20, 21, C. Now again, and we have a handful, a lot of people are saying the right ones, that's good, but don't, if you're sitting there saying, geez, did everybody get that one? I'm guessing not everybody got every one of these right, so again, don't be shy about asking. Okay, 21 was C. Next, 22, C. 23, B. 23, 25, B for 25, 26, D, 27, C, and then we skip to the next section, 29, C, 30, A, 31, 32, B, 33, you do that one? What do you think? 33, D. Not quite as many people saying the answer. 35, you do that one? C. 35 is C. 36, E. 37, D. 38 is B. 40 is C. And 45, C. C. Okay? All right. What, let's see. Okay. So what do you think? We were looking. 45. I was just talking. There's 45. Okay, now what does this mean right here? What is this asking for? What derivative? The nth derivative. That could be second derivative, third derivative, fourth derivative, fifth derivative, sixth derivative. In other words, they want kind of a formula, kind of a pattern is really what this one is. Okay, so how would you start? The derivative, right? Yeah, do the first derivative and see what you get. So the first derivative would be product rule, right? So 1 e to the x plus x left alone, and derivative of the x is e to the x. So the second derivative would be derivative of that, which is just e to the x plus, and that's, we already did that derivative, right? We just did that derivative just a minute ago. So again, it's a product, so it's e to the x plus x e to the x, and you start seeing what's going to happen every time. You're going to add another e to the x, right? And so I don't know how you go from there. I mean, what I did is I just said, well, what if I factored out e to the x here? This would be 1 plus x. And here this is 2 e to the x plus x e to the x. And if I factor out e to the x, I get 2 plus x, right? So on the first derivative, this was a 1. On the second derivative, this was a 2. I'm guessing on the third derivative, that would be a 3, because I'm a 3 to the x. So it looks like it would be C. Right? So you just kind of see a pattern. So if you get a third derivative, you get 2 e to the x plus e to the x plus x e to the x. So that's what that means. Okay? What else? 32 and 33. Okay, a certain species of fish will grow from X million to this other million each year. So it will grow from there to there. So what will happen is you start with this many fish, and then at the end of the year you have this many fish, which is more, and they want to sustain a steady catch each year. So they're going to allow a certain amount of fish to be caught, which will leave X million fish left, which is what they started with. So in other words, however many that it grew, whatever the population grew, they want to catch, allow that many to be caught to keep the population stable. Well, that would be this minus this. That's how many additional fish there are. That's how many we want to catch. Well, they did actually tell you that. Kind of surprises me that they told you that, because it could have been one where you would have had to set that up. But like I told you, one of the hardest parts of optimization, because this really is an optimization, we want to maximize the catch, is setting it up. And they're not that interested in you setting them up. They're more interested in you doing the calculus to find the maximum. So they actually set that up for you. But all they did was they took the new amount of fish at the end of the year minus how many were at the start of the year, and that's how many new fish there are, that's how many they want you to be able to catch. So that would be your C equation. I would call that C for catch. So all we're trying to do, so really all this with all the words and everything in there, they're just saying maximize that equation. That's really all. And and this is a calculator one, but if you, and don't forget if you type in your calculator, put a time sign there, but this would just be 15x minus x squared minus x, which would simply be 14x minus x squared. Well, think about it. That's an upside down parabola. The catch equation is an upside down parabola. Where's the maximum? Well, the derivative is 0. Now, so I want to talk about this a little bit. Remember, when I go through and look at these, I want to see your work, and I want you to justify it. I want you to do just like it was a free response problem. A free response problem, you have to show work, get points for each step along the way, those kind of things. On a multiple choice question, not so much. Not at all. Matter of fact, on the actual test, on multiple choice question, it's either right or wrong. This is a calculator one. A person could have just graphed that thing, traced, saw where it was, and boom, there's your back. I mean, really, if this was the actual test, you could have just graphed this thing, saw where the catch was a max, and went from there, okay? And found that answer. And so that's a strategy you should use. But on this review packet, we're trying to do something else. We're trying to review these concepts and get the idea of what's going on and so forth. So if, when we hand in these packets, if I pick number 32 out as one of them that I'm going to grade more carefully, these are the kinds of things I want to see on your paper, even though you can use your calculator. Because on the free response, even if it's a calculator problem, this stuff has to be on it. Okay, so what are we going to do with this? Do the derivative, which would be 14 minus 2x. We're going to set it equal to 0, and we would get x equals 7. Now, we need to justify that that's a max. Number line would be a good one. When you only have one candidate, you can do a number line. List the candidates, if there's some endpoints maybe, talk about where the derivative's undefined, that kind of stuff. But this would be a number line. I actually think another good justification would be say, hey, C is just an upside down parabola. So the maximum has to be at the vertex, which is when the derivative is 0, so you could actually even do that. But if you do a number line with C prime, you get positive, you get negative, and then say something like C is always increasing before 7 and always decreasing after 7. So 7 million is what X should be, which is, it says what's the number of fish that should be left, and that's what X is. X is how many are going to be left after the catch. And so X would be 7. Yeah, I mean, in your pack, in these packet problems, I think I've said that before, but I want to keep reiterating that there are some problems where you don't, I mean, there just isn't anything to show. I mean, we'll do one here when we do number 33. There really isn't anything to show on 33. Okay, what I will do is be looking for kind of some completion, so I'll be looking through your work kind of quickly, but I'll also pick out a couple of, in each packet, I'll pick out a couple of multiple choice questions, probably a free response or so, that I want to look at the work more carefully, and I'll pick out ones where I know there should be some work, like on this one, right? Even though it's a calculator problem, and I understand if it's a multiple choice one on the test and you can just type in your calculator and get an answer, that's fine. But we're really practicing for the free response, and we're practicing these concepts, so that's why I'm wanting you to go through this, okay? Because if it's a calculator one, I think I've said this many times, whether it's on a free response question, if it's a calculator or no calculator, your work looks almost exactly the same, okay? The only difference would be if you have to do a bunch of algebra to solve an equation. If it's a calculator one, you can just let your calculator solve the equation. But you still have to have those things in there. Now, we're going to be talking next week especially more about free response questions, okay? Because we haven't spent a lot of time in the free response questions, so we'll be talking about those. On the AP test, that's half your grade. Half your grade is free response questions, half is the multiple choice. There's 45 multiple choice, there's only 6 free response, but the grade is based on half of that, so it's a very important part of it. All right, so 33. Now in 33, I don't think there's really any work to really do here, okay? You're just asked, he's got a graph, horizontal asymptotes, which of the following is true? Well, okay, what about this one? What's this mean? F prime less than 0, what's that mean? slope is negative, right? Slope, gotta be careful, that slope is decreasing, the graph is decreasing, right? F is decreasing. That means the slope is negative when x is positive, so that means right through here. Is that true? Definitely true. The slope is definitely negative that whole time. So it's definitely, 1 is definitely true. Limit as x goes to infinity, so that means when we get way out here, does the slope equal 0? Now, technically that's not right. It doesn't mean the slope equals 0, it means what? Approaching 0. When you do a limit is what's it approaching. So as x goes out here to positive infinity, is the slope approaching 0? Yes, it's leveling off. It never will equal 0, but it is approaching 0, and that's what that means. A limit problem, when we say the limit equals 0, what we're saying is it won't necessarily be 0, but it's approaching 0. So 2 is correct. So now the only question is 3 correct? As we go to negative infinity, which is out this way, is the slope approaching 2? No, the slope again is approaching 0, right? The slope is approaching 0. It's leveling off. That's what happens many times with a horizontal azimuth. So that one is not true. So it's got to be B. Okay? So again, there's really not any work that would be shown on that problem, I understand. Okay? Others? '20. This is one where they're testing your derivative skills, little algebra skills, and remember on the no calculator parts, that's going to be always a big emphasis. You would expect to have to do that. And then somebody brought up in the other class, and I think I mentioned this before, just because it's a calculator section doesn't mean you use your calculator, right? There's a lot of, well, think about the one we just did. That was in the calculator section, and that didn't use the calculator at all. The calculator couldn't have helped you at all. 33. It was in the calculator section. The calculator section just means, hey, if you need it, you can use your calculator. Okay? All right. So this says for x less than or equal, okay, what's that all about? Anybody even pay attention to that? Does that even matter? That's all it is. Now, to be honest, most of the time it doesn't do that. Usually we call that the natural domain. If they give you a function, we'll just assume that it's always defined. So anything that would make it undefined is just not part of the problem. So kind of surprised they put that in there. A lot of times they wouldn't, but yeah, that's all it does. X less than 1 basically means it's between -1 and 1, right? As long as it's between -1 and 1, we won't have a negative inside the square root, so that's good. All right, now I would put parentheses here, to be honest with you, natural log item, because I think that really emphasizes there's an inside, because that's going to be important here, the derivative of the inside, we're going to need the chain rule. You know, it's kind of like in trig class when you write sine x. I mean, when I taught trig, I wrote it that way all the time. I always wrote sine x. I never put parentheses on it. As soon as I started teaching calculus, I started writing it that way, because it became pretty important to understand that's a function, that's an inside of the function, and so forth. Okay, so what's the derivative of this? Then, what's the rule for ln? 1 over, we leave that alone. Derivative of the inside, which means we're now needing to do the derivative of this. Right? That's the inside. Well, how do you do that? 1/2. Inside left alone. -1/2 times the derivative of its inside, which is -2x. So you got to be careful, because if you do everything right there except forget the negative, you're going to think that the answer is A. If you forgot that negative, and do everything else right, including all the algebra we're about to do, you would get A for an answer, just by forgetting that negative. Okay, so it's -2x. All right, so what do we got? Well, let's see. This would be it's just a bunch of stuff multiplied together, really. And this 2 would cancel that 2. This negative power is going to flip to the bottom. Now, I still noticed, what was it? I think it was on the last quiz. I noticed we had a square root. I can't remember. We had a square root, and I think somebody put it to the -2 powers instead of the 1/2 power. Or maybe it was we had a negative, what should have been a negative power, and they made it a 1/2 or something. So you still have a few people who are mixing that up. But anyway, we've got negative power, which means this is gonna flip to the bottom. So what's gonna be left on top? Negative, well, I canceled the twos. So just negative x, right? That's all will be on top. And what will be on the bottom? There'll be a square root of 1 minus x squared. What about this when we flip it down? Also a square root of 1 minus x squared. So what's a square root times a square root? Just 1 minus x squared. So that would be it. And then we look up here and that's not any of it. Because of that negative, right? Remember what I said the other day. A subtraction, if you just take out a negative, it flips it. Because here's what would happen. So the top is negative x. The bottom, if I take out a negative 1, then this would become a negative 1 here. And this would become a plus, right? And then this negative would cancel that negative. And so we just have x. And then the bottom would flip around to x squared minus 1. So that's b. So that's where you get b. Okay? So that's the derivative rules. And then there's some algebra simplifying you have to do to get the answer. When we were studying for the gateway test, remember I made you kind of wanted you to do some simplifying and stuff. Now I wouldn't have made you do this. This would have been just fine right here. But, and I think what I said along the way, when we get to the midterm and we get to the multiple choice, you have to do some of the simplifying to match your answer. Okay, so that's how to check your algebra. All right, another one? Anyone else? 26. A normal line to the graph of a function is defined to be the line perpendicular to the tangent line. So if we have a function and we have a tangent line, the normal line would just be perpendicular to that. So it's got to go through the same exact point, but its slope is what? Opposite reciprocal. So we would just do everything we would normally do for a tangent line problem. We need our point and we need our slope. The slope is going to come from the derivative. But once we find our slope, we'll just do opposite reciprocal before we plug it in. So we need the point. Oh, they gave us a point, or part of the point. They gave us 3. How can we find the y value? Plug the 3 into that equation. That'll give us the y value. That would be this point right here. So we put a 3 in there. 3 times 3 is 9, minus 1 is 8. Cube root of 8 is 2. So there's that. Now all I need is a slope, which I get from derivative. So that'd be x squared minus 1 to the 1/3 power, right? Not negative 3, but 1/3 power. So I got to do that derivative. So that'd be 1/3 x squared minus 1 to the negative 2/3. Root inside is 2x. What do I do with that? Plug a 3 in. So, okay, so this would be 2 times 3 would be 6. 6 times a third would be 2. And then this would be 1 over. So, is this calc? No, this is no calculus. So now I got to plug a 3 into here. So 3 squared is 9. 9 minus 1 is 8. What's 8 to the 2/3? That is 4. Because what you do is the third, the 3 on the bottom would be a cube root. So we do that first, do the cube root of 8, which would be 2. And then the number on top is the power. So that'd be 2 squared, so that'd be 4. So 2 times 1/4 is 1/2. So the slope is 1/2. But that's the tangent line slope, right? So the slope we want is negative reciprocal, which would be negative 2. So we put a negative 2. Okay, so what we were looking for was equation of a line, and anytime we have equation of a line, we want to do point slope. We had the point, but we had the 3, we plugged it in to get the y, and then we needed the slope, which we got from the derivative. But the slope of the tangent line is a derivative, so that's a half, so the normal line would be opposite reciprocal. Now it's just a bunch of algebra we distribute. So we get y equals negative 2x plus 6 plus 2. Y equals negative 2x plus 8. And then we look at our different answers and add the 2x over to that side. Y plus 2x would equal, which is. So again, multiple steps along the way to get you where you needed to go. But again, the secret to those is just think of it one step at a time. Don't get overwhelmed by normal line, tangent line, perpendicular, all that stuff. Just take it one step at a time. What do they want? They want the equation of a line. Okay, that means point slope. Write that out. Need a point. Okay, they gave me a 3. How can I get the y? You know what I mean? Just think about one thing at a time. That's how you get through. Another one? We don't have to, but we got a little time. Aha. This function has 1 0 in this interval. The derivative at that point is what? So we're going to need a derivative. Although I don't think that'd be the first thing I would do, but it doesn't really matter what you do, what order you do. What about this first thing it says? What's that mean? Set what equal to 0? The original. We don't do that very often, right? I mean, I can't hardly think of a time we set the original equation equal 0, but that's what they want. They're telling us that this function has a 0, which means where it crosses the x-axis, which means where it is 0. We don't rarely do that for any of these calc type problems, because what does that tell you? It just tells you where the function crosses the x-axis. I mean, so maybe you're interested in that. This one we are. We've been really interested in where derivatives are 0, because that's where the slope is 0, which is like a max or linear. We've been interested in the second derivative 0. What's there? Inflection points are when the second derivative is 0. So we've been really interested in those points, but not using the original. So we got to solve that. Well, that's what your calculator is for, right? So do a solve. Do a solve with that, and do a vertical bar, and limit it between 0 and 1.4. Okay? Do a solve and limit it in there. And what do you get? 1.042, does that sound right? Okay. So that is the place where it has a 0. Now, what do they want? The derivative at that point. Now, here again, if this was the actual test, I don't know that you'd have to write down anything. I mean, on the test, you don't have to write down anything in the multiple choice. I mean, you will probably, you'll do some work and stuff, and then when I pass back the test, you can look at the work. But as far as me grading it won't matter. So you can do everything on the calculator here. If this is a free response, you would have to write this stuff. So that's what I want to see on your paper on this. Even though you could have sat there and done everything on your calculator. When I go through and look at it, you just have an answer down there. I don't know. I can think you just copied it. Right? I mean, I want to see what. So on this one, I want the rule on the free response is if you're solving an equation on your calculator, you have to have an equation on your paper. So I'm solving this equation. I need it on my paper. Also, on the free response, don't ever write calculator lingo. Don't ever write solve, stuff like that. Don't do that, okay? But you would write that out, and then you'd have this. You don't need to show how it got it or anything. You just write this, okay? That's fine. Now, what do we want? We want the derivative. Now, you could do it on your calculator, but it's secant squared. Oops. Sorry. What is it? 3 to the x, right? Secant squared of 3 to the x times the derivative inside. What's the derivative of 3 to the x? 3 to the x times ln 3. Remember that? Now, again, since it's a calculator one, you could have let the calculator do that derivative. Then you wouldn't have forgot about the ln 3. But otherwise, you might have forgot about the ln 3, right? And I'm guessing the calculator, it doesn't look like this. Did anybody do it on the calculator? Probably has an ln with a cosine squared, probably. It probably didn't do secant, it probably did cosine. Okay, and now we want to plug 1.042 into that. And you wouldn't have to write that all out. You could just, you have your f prime written out, and now you're going to do f prime 1.042, and now you plug that into your calculator. And I think it comes out to C, 3.451, right? And of course, look what they did to you. They put 1.042 there, B, thinking that some of you will forget what you were doing here, and you'll solve, and you'll get to here, and you'll see it, and then you'll think that your answer is going to be good. All right. Well, let's move on. Let's, if you've got some other ones, there'll probably be some time here at the end of the period that you can ask about those, but we need to turn to our book here today for a little bit. Section 4.8 starts on page 275. Oops. I don't know what that would be for. Maybe if it was too bright. It's just weird. Okay. Yeah. Well,
Does he get off his week?
I need to get out. Homework track. Okay, when I was on this, it was there. All right. Now, next week we have the chapter 4 no calculator quiz. And what that quiz is about is the big ideas in chapter 4. Okay, chapter 4 is the culmination of all the work we've done with derivatives. And it is applications, where are they useful, and so forth. And so it's a lot of short answer, true, false, those kind of things. Some of you will like that, especially coming off of the last quiz, which was setting up story problems and a lot of calculation and that kind of stuff. This will be on the other end of the extreme. Somebody in the other class was saying, "Oh, good, I can make flashcards." Not that that's a great thing, but it's something that you can literally study. I mean, you know what I mean? You can memorize a little bit and so forth. I mean, so for some people you will like that. That would be a nice change. Matter of fact, I will tell you right now, 3 of the questions that will be on next Wednesday's quiz. I'll tell you the exact question. Okay? One of them is state the extreme value theorem. That's going to be one of the questions. There's also going to be a question that says state the intermediate value theorem. And there's going to be a question that says state the mean value theorem. Guaranteed to be on the next quiz. Okay? So we're going to do the first 2 of those today. First one is the extreme value theorem. Just from the name, you should be able to kind of tell what it's about. It's about extreme values. Now the title of this chapter is, or this section is why continuity matters. So the emphasis in this section is continuous functions. Continuous functions. Now if you remember from an earlier section, a continuous function has to meet 3 criteria. It has to have, the function must be defined. You don't need to write this down, but the function must be defined. You can't have a hole in the graph. You can't have a vertical asymptote because the function's not defined at that spot. So those would be discontinuous. Now, the common sense way of thinking about continuous is you never have to lift your pencil. No breaks, no jumps, no gaps. Okay? Well, that would, no holes, right? And so those would fail it. So why do those fail it? Because the function's undefined in those spots. The second thing that has to happen is a limit must exist. Okay? Everywhere. Well, that would be this situation, right? Where the cars don't meet. A break, a gap. Can't have that if it's going to be continuous. And then the last example was, what if you had this? Remember the diner burned down and then they rebuilt it in a new place? This one fits the first 2. The function is defined right there. There's an output. The limit exists. The cars meet right there. So what's wrong with this one? What's that? They have to be the same, right? The limit has to equal the output, right? So you have to have an output, you have to have a limit, and those 2 have to be the same. So it has to meet those 3 things to be a continuous function. It's something we did back in chapter 2. Okay? But essentially, what has to happen for a function to be continuous is you never have to lift your pencil. No gaps, no breaks, no jumps, no holes, that kind of thing. All right. So if a function is continuous, then that's very nice to know. If they tell you, and you know we've got a lot of problems where it says f is a continuous function, that's great, that's good. Because it tells you it's not undefined anywhere, it doesn't have any vertical asymptotes, right? I mean, that's a good thing to know. So why is it important to know if a function is continuous? Well, there's 2 reasons, for sure, that we're going to do, and they're these 2 theorems. So the extreme value theorem says this. Let f be continuous on the closed interval AB. Now, sometimes I've said that as if f is a continuous function on the closed interval AB. And then, so sometimes we say if, like an if-then kind of statement. And sometimes we say it this way. So when I ask you on the test that I want you to state the extreme value theorem, I do kind of mean word for word. Now, there are a few words you could interchange and still have the same meaning, but you got to be careful. You don't want to go too far off of the right word. Okay? We'll talk about some plain English, ordinary ways of thinking of these theorems to help understand them. But when I ask you to state the theorem, I want it to be stated the way we've done here. All right? Because too often when you try to go off kind of on your own, when we kind of do our own kind of common sense way of saying them to make sense to ourselves, we're not being mathematically precise, so we got to be careful. All right, so let f be continuous on the closed interval AB. Then f assumes both a max value and a min value somewhere on that interval AB. So this is not any great, I mean, this is the simplest of the 3 theorems by far. This basically just says, this is called an existence theorem. This guarantees that if you have a continuous function on a closed interval, that there's going to be a high point and a low point. That's all it says. Now, what if you had a horizontal line at 7? Is that a continuous function? And let's say you were going to look at that from 2 to 3. Is that a closed interval? Is there a high point on that? Is there a max value? What would it be? 7. Is there a minimum value? 7, right? It's both. It's a max and a min. So the high point and the low point could both be the same thing. Okay, so that would not violate this theorem. Okay, but this just guarantees that if you got a continuous function on a closed interval, there's got to be a high point, got to be a low point. Okay, now what are some of the questions that you might be asked on the homework? And you'll see when we get into these. And you guys that were in computer math, anybody in here in computer math? Oh, that's right. We only had one. Yeah, I thought maybe some cross. Second, third block.
Are you serious? Maybe we should have a class.
There's a lot of individual attention. All right, so, that's cool. Well, that's because none of the rest of you lazy bums signed up for it.
Microbiology. Yeah, I had walking business.
I had to have a lot. Yeah. To rest up, 9 weeks, I needed 9 weeks to rest up for calc stuff. Well, anyway, if you would have signed up for computer math, you would know a little more about this if-then statement kind of stuff of what we're going to talk about. And the example I used in computer math was this. If your parents said to you, if you get an A, then I will buy you a car. Fat chance of that happening. But if you get an A, then I will buy you a car. That's kind of like this, an if-then, kind of like a promise. That's what this is saying. If a function's continuous on the closed interval AB, this is promising that there's both a high point and low point, both a max value and a min value. So if you get an A, then I will buy you a car. So what happens if you get an A? You get a car. I mean, if they didn't, then they would definitely be violating that promise. That would break that promise. If you ever found a continuous function on a closed interval that didn't have a high point or low point, that would violate this theorem. That would break this theorem. It's not going to happen. This is proven to be true, and that you're not going to be able to find it. Okay? But what happens if you don't get an A? Don't answer, Sam. What happens if you don't get an A? Let me say that again now. Here's the promise. If you get an A, then you get a car. So what happens if you don't get an A? Yeah. You might get a car. That'd be some kind of parents. But you might get a car, and you might not. Because did the promise say anything about if you don't get an A? It didn't. Now, you're right that probably the assumption there is, and I'm sure that's what they meant, was if they said, if you get an A, then I'll buy you a car, I'm sure it meant if you don't get an A, you don't get the car. But that's a different statement. Okay? So, if the statement is, if you get an A, then I'll buy you a car. This is called the hypothesis. The first part's the hypothesis, and the last part's the conclusion. If the hypothesis is true, then the conclusion has to be true, if that theorem's going to hold. If the hypothesis is false, the conclusion could still be true. It doesn't say anything about what happens if the first part's false. Okay? The conclusion could still be true. You could have a function that's not continuous, or doesn't have a closed interval, that still has a max and a min value. It still could. It's just not guaranteed to happen. Okay? So that's going to be an important thing in some of the questions as we go along. All right, so that's the first one. Here's the second one. Oh, hi. All right. The second one is the intermediate value theorem. Now, when you hear the word intermediate, what do you think of? In the middle, or actually not middle, but in between. In between. Okay? There's a difference between in the middle and in between, right? In the middle means halfway, right? In the middle. Intermediate really just means in between. Okay? In between. So extreme value said something about extreme values. Max is a min. Okay? This is going to say something about in between values. Okay? The intermediate value theorem. Now, your book, when it talks about this, calls it the IVT, and the extreme value theorem calls it the EVT, so when you see that, you know what they're talking about. Okay, here's the intermediate value theorem. Let f be continuous on the closed interval AB. Let f be continuous on the closed interval AB. And let k be any number between f of A and f of B. So that whole sentence is the hypothesis. That's the first part. Function has to be continuous. You have to be on a closed interval AB, and k can be any number in between f of A and f of B. Then there exists some c between A and B such that f of c is equal to k. Okay? Now, that one's a little more complicated. So let's break it down. I mean, let's talk about the different parts here. Now, we actually just did, I think the other day, dealing with Newton's method, and it was on the sample exam. We did a problem that would involve this. Matter of fact, on sample 2, problem number 3. Let me read you what the answer book says on sample 2, problem number 3. It says, this question is testing the student's knowledge of the intermediate value theorem. Now, my guess is you guys got, a lot of you got that question right and didn't know anything about the intermediate value theorem, right? That was the problem that talked about, gave you, what was it, f of negative 5 was 3, and f of negative 1 was down here at negative 2. And it asked something about the 0 of that function, and you said what? It had to be, well, oh yeah, it actually gave you the graph. Did it give you a graph? No. So it had to, so what did you say? It had to be, oh, and then it gave you different choices. But, and you were looking for something that was between negative 5 and negative 1. You knew it had to cross somewhere in between them. Now, why is that? Since it's a continuous function, if it's going to go from here to here, it's got to go through here, right? Now, it could have went up here first, right? And then come way down here, and then went here. But it's got to hit 0 sometime. Not only that, but wouldn't the function have, now we were interested in the x-axis because we're often interested in zeros of a function. But wouldn't it also be true that that function would have to go through there? Wouldn't that function also have to go through there? Wouldn't it also have to go through here? Matter of fact, wouldn't it have to hit every y value between there and there? I mean, if this function is continuous, means no jumps or gaps or breaks, if it's going to go from here to here, call that the starting and the ending point, That'd be f of negative 5 and f of 1, negative 1. Oh, wouldn't that be the f of a and f of b here? Wouldn't our closed interval be negative 5 to negative 1, right? Let k be any number between f of a and f of b. Here's f of a and f of b. Let k be any number in between here, any y value. Isn't there somewhere that it will have to hit that y value? There's somewhere in here, somewhere in between a and b, somewhere between negative 5 and negative 1. There's got to be some c value that when you plug it into the function would give you one of these y values in between here. That's what that's saying. So if you were going to put this into kind of an everyday language, it would be if the function's continuous on a closed interval, the function will have to go through every y value between the starting point, and this is really key. The f of a and f of b is probably the biggest thing we mess up on intermediate value theorem. F of a is the output at the left edge, and f of b is the output at the right edge. Call those your starting and ending points. The common ordinary language would be if a function's continuous on a closed interval, the function has to hit all of the y values between the starting point and the ending point. Now, isn't that kind of common sense? If I start in Grand Island and I'm on Highway 30 and I end up in Kearney, what's that mean? I had to go through all the towns and all the spots between Grand Island and Kearney. Now, if I started Grand Island, I could have headed east and went to Columbus and then turned around and came back and ended in Kearney. The intermediate value theorem says I hit all the points between my starting point and my ending point, Grand Island and Kearney. Yeah, I hit some other points too. Right? Remember on this problem we were saying that the function could go up here and then come back down and then go down here and then go here. But what the intermediate value theorem doesn't talk about those points. It just says from your starting point to your ending point, you got to hit all those in between. Okay? That's what it says. So if you wanted to do, just to jot down that something like that just for yourself to help you understand it, that might be a good idea. So here's an example here. Okay? There's my starting point. There's my ending point. The intermediate value theorem says that this blue graph has to go through all of the y values that are in the green. Sure, it goes through some other y values too, but that's not what we're talking about. We're just talking about you stop this at any k value you want. Stop it at any k value you want, any point in between here. There's got to be some c in between here that will hit that point. And sure enough, right here, there'd be a c right about there that would hit that point. Now, it might be more than one. If I let k go, right, it might hit it more than once. Come on. Come on. There you go. Right? If I look at this k value right here, there's a c right here that hits that point. There's a c value right here that hits that point. There's a c value right there that hits that point. So it could hit it more than once, right? I might start in Grand Island, I come to Kearney, and I realize, oh, I forgot something in Shelton, and I go back to Shelton, and then I come back, right? I hit Gibbon like 3 times. But it just says, if I go from Grand Island and end in Kearney, I have to hit all those points in between. Okay? Right? Unless, what's the only way? If I start in Grand Island and then what? I get to Shelton and then I beam myself to Kearney?
It's possible.
What?
What if you take a plane and fly all the way around the world and then end up in Kearney?
Well, then I wouldn't be on Highway 30 anymore.
True.
You see what I mean?
Still do
But
it.
well, what about this? What about the situation I just said? What if I start in Grand Island, I get to Shelton, and I beam myself to Kearney? It's not a continuous function anymore at that point. Because what? You got a gap. You got a break, right? So again, that wouldn't violate this theorem because it's not a continuous function. It doesn't make a promise about hitting all those points in between if I beam myself there, right? So it's not a continuous function. Okay, so if it's a continuous function on that closed interval, I have to hit all those y values in between. Okay, so that goes to what we did with Newton's method. We talked about finding where the roots are. Well, if you get a positive output here and a negative output here, if you know it's a continuous function, the intermediate value theorem guarantees you that there's got to be a root in between them. Because that continuous function, if it starts here and ends here, it's got to hit all the points in between, so it's got to hit a root. Okay? Now, again, that seems like just common sense. You guys kind of understood that before we ever talked about intermediate value theory. We don't do a lot of theory in this class. We don't get into the theory behind the calculus that often, but this is a couple sections where we are going to dive into a little bit. These are some of the more important theoretical foundations in calculus. So, continuous function. All right, one problem. Oh, we got all kinds of stuff. Perfect. So let's take a look at this problem right here. I'm going to make one up here and ask you a couple questions, and this is what your homework is going to be about. So let's say we have this function right here. Okay, we got this function, and I'm going to ask you a few questions about it, and this is on the interval 0 to 9. Okay. Well, no, wait a minute. My questions will be different depending on the question. Okay, question 1. First of all, what's that function look like graphically? We should all know that. Sideways parabola, starting at the origin, like so. Okay, square root of x. Only positive outputs, right? You can't put any negatives into the square root. We only get positives because that's the top half of the parabola. Okay, so square root of 9 is 3 and so forth. Okay, so in this first question, what does the EVT say about f on the interval 0 to 1? The closed interval 0 to 1. What does the these are some of the questions I might ask you on the quiz next week. So these are some of the questions that will be on the homework. What does the extreme value theorem say about this function on the interval 0 to 1? Say it again. That's all the extreme value theorem says. It guarantees there's a max value and a min value. Doesn't say where they are. It just guarantees that there is a max value and a min value. Why? Because that's a continuous function on a closed interval, right? And it's important to put that in there. What does the extreme value theorem say? Since it's a continuous function on a closed interval, it says that there's a max and min value. Now, where are they? That's another question, right? Yes?
If you didn't have the interval, it would still be continuous since it's not defined for anywhere left from 0.
We're going to get into that here in a minute. Okay? Now, yeah, go ahead.
I was going to ask if we're ever going to be put in a situation where we'll be given a function that isn't continuous and yet have an interval set somewhere that it's continuous all the way.
Hold that thought. Well, we just did right there. I mean, well, yeah, no, yeah, I know what you're saying. We'll do it. We'll do it one method. Back to where the max and min is. See, that's another question, right? As a matter of fact, that'd be a great question for the quiz next week. We talk about big ideas in chapter 4. One of the really big ideas was optimization. And the main crux of optimization is where do you look for max and min? There's 3 places. The endpoints, when the derivative is 0, and the derivative is undefined, right? When the derivative is 0, when the derivative is undefined, and at the endpoints. That's where you would look for the max and min. The extreme value theorem just guarantees that there's got to be one. Now, we did have problems where there was no max, or whatever. Well, that's because it didn't have an endpoint maybe, right? There was no closed interval. Or maybe the function was undefined or something like that, okay? But not very often did that happen, okay? But we did have problems that had a max, but maybe didn't have a min or something like that. Well, that was because they either weren't continuous or they didn't have a closed interval. All right, and that's what I wanted to get into next. So look at number 2. The second question I want to say. What if you were looking up at, and this might be a little bit towards what you're saying, Nicholas, on the interval 0 to infinity, this thing is continuous, right? This function's continuous from 0 to infinity, but there's no max value on that interval. The question says, does this contradict the extreme value theorem? Why not? It's not a closed interval. It's continuous, but it's not a closed interval. And to be honest, you should never, hopefully you never answer any of these questions saying, yes, it does contradict the extreme value theorem, because you can be famous if you can contradict the extreme value theorem, because it's proven to be true. So it does not contradict it because it's not a closed interval. All right? And likewise, the other way would be, what if you had this interval? But if you look at it from 0 to 1, there's no, it's not a closed interval, right? Because we didn't include 0. There's no minimum on that interval, is there? I mean, what would be the minimum? If you don't include 0, you'd have to get really close to 0. Well, you could get infinitely close to 0, right? And never have a minimum value. You get closer and closer, smaller and smaller, but you keep getting smaller, but if you don't include 0. So there's no minimum there. But that's not a problem because it's not a closed interval. So the theorem doesn't promise the same. Okay, here's the trickier one. So let's say we were on the interval 0 to 9. Show that the IVT, the intermediate value theorem, holds for k equals, k equals 2. Show that the intermediate value theorem holds for k equals 2. So to show that it holds, we have to address all the different parts of the intermediate value. So go back to your notes there. And we would have to address something about the interval. We'd have to address something about it being continuous. We would need some information about f of A and f of B. We would need something about this right here. Okay, we need to do something with all of that. Okay, so where do you want to start? We have a closed interval. It is continuous on that interval. 0 to 9 would be out here somewhere. Right? It is continuous on that interval 0 to 9. No. Now, what you everybody hear what Sam said? He had this 2 is in between 0 and 9. What's the flaw in that? K is a y value. K is a y value. So it needs to be between the two y values. So I heard somebody say f of A. We need to address f of A and f of B here. So what's that mean in this problem? We need to talk about f of 0, or we need to talk about f of 9. What's f of 0? 0. What's f of 9? 3. Those are my y values. In other words, right here is 3, and right here is 0. So the intermediate value theorem would be talking about there. Well, where's K? K is in between them. So I think a picture would be helpful here. So what did we say? That curve somewhere has to hit 2. There's some C value in between 0 and 9 where that hits 2. So in other words, isn't that what we really need to find? We need to find what that is. Well, how would we find where that is? Find when the output is 2. Remember we said 2 is a y value. So what we want to do is we want to find what input would give us that y value of 2. So we take our function, set it equal to 2. So you square both sides, you get 4. And sure enough, 4 is in the interval 0 to 9. So we just addressed all of that. We've said, okay, it is a continuous function on the closed interval 0 to 9. K equals 2 means that the function somewhere has to hit 2. K is in between f of 0 and f of 9. It's between my starting point and my end point, which is 0 and 3. And there is a point in between there that has an output of 2, and that's it when x is 4. So that's the C value where it equals that. Okay? So that would be showing that using the intermediate value theorem. So when I say there's not any real problems or calculations on this no calculator quiz, I mean some small calculations like that might be on, but they're all going to have to do with these theorems.
Same with the picture and the equations.
Well, I know, I think the picture helps, but I think if you had all this stuff and you said some things about it, you would have to have the picture.
That'd be necessary.
Yeah, but you would need to address the. But I like having the picture because I think that makes sense as far as hitting all those points. That's helpful. Okay, so let's get started on the homework here, and I think it will help probably for us to just kind of go together through some of the first parts of the homework. So I want to do that with you. So we're looking at section 4.8 homework here. right, section 4.8 homework, which starts on page 279. Ryan, did you? All right, so the first two questions that you were dealing with graphs F and G here. Now clearly those are not continuous. I mean, they got all kinds of issues with breaks and holes and all kinds of stuff going on. But there are parts of them where it's continuous. So we were talking about this earlier. Okay, so that's the first question. Where is F continuous? So let's just run through F and then you can do G on your own here in a minute. But so F would be, let's start over on the left. And what intervals would F be continuous? -4 to -3. Now, would you include -4? Yes. Would you include -3? Why not? Because there's a hole, there's a gap, right? I mean, it's just not continuous at -3, so you wouldn't include -3. Okay, then where? -3 to -1. Would you include either in? Because there's a gap here and there's a break here. Right? So it's not continuous there. But from -3 to -1, this function's continuous. You never lift your pencil. Okay? So no problem. Okay, then where? -1 to 1. Now careful here. -1 to 1, would you include either of those endpoints? No. The question is not if it's defined. The question is it continuous? And that has to meet those three criteria. At -1, is this continuous? I know this is filled in, but that doesn't matter. At -1, there's a break. The cars don't meet, right? So the limit at -1 does not exist. So it is not continuous at -1. It's continuous in between there. And then at 1, it's not continuous because there's a break. Okay? So it's continuous from -1 to 1, but you wouldn't include either input. And then where? 1 to 2, it's continuous, but not at 2 or 1. And then from 2 to 4, but so in other words, you wouldn't include any of those endpoints except the first one, because there wasn't anything on the other side of it. It's everything's fine there. So -4 you would include, but none of the rest. Okay, so it's a similar thing you would do in number 2. Okay, all right. So let's jump down to number 7. So number 7 says, does the conclusion of the extreme value theorem hold from -4 to 4? Now clearly on this one, the function is not continuous. So the extreme value theorem doesn't make any promises, right? I mean, you look at graph F, you did not get the A, right? The question is, do you get the car? Right? Remember, we said you don't get an A. You might get the car, you might not. That's the conclusion to that promise. Well, what's the conclusion to the extreme value theorem?
It's actually
Oh, is it intermediate?
yeah.
Well, then I want to skip to number 9. Hey, welcome back. Okay, intermediate value theorem. Okay, so then we'll do it. So the intermediate value theorem. All right. So does the conclusion hold? That's the question. Right? Does the conclusion hold? Well, what was the conclusion of the intermediate value theorem? I mean, let's put it in everyday language. What's the conclusion of the intermediate value theorem? Just our common sense way of thinking about it. That's the hypothesis. What's the conclusion? You hit all the y values. We're doing intermediate value theorem. The conclusion of the intermediate value theorem is you'll hit all the y values between the beginning and the end. Remember the f of a and f of b. Okay, let's look at this picture again here. So, great timing, Nolan. You're right. Uh-oh, future basis. Okay. The conclusion of the intermediate value theorem is that between the starting point and the ending point, we will hit all of the y values in between them. That's the conclusion. Okay? The hypothesis is it has to be a continuous function on a closed interval. We have a closed interval, negative 4 to 4, but we clearly do not have a continuous function. So there's no promises that the intermediate value theorem is going to hold. There's no promise that we're going to hit all the y values between the beginning and the end. Okay? But the question is, does it? Okay, it might, but does it? Well, let's see. What do you think? Yes or no? Okay, some are saying no. Joe, why are you saying no? Where at? Where? The negative 1 and the 2. I'm not, the y or the x you're talking about?
Oh, the 1 and the 2.
Right in here? You're worried about this break right here. There are no y values in between here. Would you agree with that? Sam, you say it doesn't matter. Okay. You're close. Now, let's talk about the first part of that you said was correct. And remember, and don't feel bad, you guys that missed this, because it happens all the time. The thing I said was the most common thing people are going to forget about is the intermediate value theorem only talks about from f of a to f of b, the beginning and the end. So we don't have to worry about this up here, right? Where's the beginning? F of negative 4. Where's the end? F of 4. Here's f of negative 4. The part you missed was what's f of 4? That's f of 4 right there. You were looking down here, right? The function begins here and it ends here. Remember, it's f of a and f of b. Here's a and b. So it's f of, this is the most common thing people forget. Now, so I think what Joe was doing, and many of you who were shaking your head yes, was thinking, oh, it has to hit all the y points. So you were thinking from the lowest up to the highest, and that's not what it says. It says from the beginning to the end. Okay? So here, and Garrett had a really good idea in the other class. He said, kind of like my picture here, kind of like this picture, where it draws these dashed lines. He said he thought that would be helpful just to do that. And I think that's maybe a good idea. So identify your beginning and your end point, and then draw these dashed lines. So the intermediate value theorem says it has to hit, the function has to hit all the y values in between them. Does it? I think it does. Right here, there's a gap, but that dot fills it. And then you go up here, there's a hole there, but there's a point there. You go up here, there's a hole, but there's a point, right? So I think the blue graph hits every y value between the beginning and the end. Y value. Okay? So the answer here is, does it hold? Did you get the car? Yes. You didn't get the A, but you still got the car. Okay? But you might or you might not. But the conclusion held. But it didn't have to. The conclusion only has to hold if the hypothesis holds or is true. Okay, then let's do the same thing on number 8 for G. Yes or no? Beginning, right here. Ending, right there. Do we hit all the y values in between there? I believe we do. So it's yes. Even though we don't hit this one down here, it doesn't matter. These points down here do not matter. Okay, number 9. Does the extreme value theorem hold? For F. What's the conclusion of the extreme value theorem? There's a max and a min. Now, this is not a continuous function, so we're not guaranteed to have a max or a min, but we still could. Do we have a max? What is it? We have a max of 2. What's our min? So yeah, we did have both a max and a min. So there's the extreme value theorem. Okay, what about G? We have a max of of 2, do we have a min? No. You would not have a min because you can never get all the way to negative 2 here. It doesn't include negative 2, negative 1.9, negative 1.999, negative 1.9999, on and on and on. Somebody in the other class said, what about negative 1.9 repeating? What about it? What is negative 1.9 repeating? Well, it's not even limited. Well, let's just ask a simpler question. What's 0.9 repeating? Well, it's 0.99999 forever, but it is 1. Not close to 1, it is 1. Do you know that? Think about it. Yeah, well, what's 0.1 repeating? Maybe you didn't know this, but it's 1 9. 0.2 repeating is 2 9. And here's the one that usually convinces you. 0.3 repeating is 3 9s because it's 1/3. We know that, right? So 0.9 repeating is 9 9. 9 9. It is 1. So anyway, but their thought was that would be the number right before negative 2 would be negative 1.9 repeating, but it's not. It actually is negative 2. Okay, so you could not get. There is no minimum value in this one. So the extreme value theorem conclusion doesn't hold, but that's okay. It wasn't promised to hold because this is not a continuous function. All right, so that's why it didn't hold. All right, so on your homework, so I'm going to let you go with the rest of these. On your homework, it asks you, it says, does the conclusion hold? And then you might say no, and it might say, why doesn't it hold? Well, if it doesn't hold, it's because something in the hypothesis wasn't true. Either the function wasn't continuous or it wasn't a closed interval. I mean, basically, those are about the only 2 things that could be a problem. So you'll see some of the same answers showing up over and over. Now, when you get to number 11 through 16, they're talking about the function 1 over x, which, Nicholas, goes back to something you had said earlier one more time here. That's this function right here. It's a hyperbola. Looks like this, has a vertical asymptote here. This function is continuous in some places. Like from here to here, this is continuous. But it's not continuous at 0. It has a vertical asymptote. There's a lot of places it is continuous. Okay? And so it asks you some questions about the theorems in there. So they're pretty straightforward. So the homework doesn't take a whole long time. So I would suggest working on that the rest of the time. And then continuing in the sample 2, maybe get into the free response questions a little bit, doing that. And here, before you leave at the end of the period, I'll give you the take-home quiz. So it's going to kind of look like this over the course of the next several days. So tonight, finish this homework, kind of work on sample 2 a little bit. If you're going to be really busy this weekend or whatever, want to work on the take-home thing tonight, you can do that too. Okay? Tomorrow we'll have some time in class to work on the sample 2 free response, so you don't have to get those done by tomorrow. Okay, we'll have some time, but we'll probably take some time to answer some questions about it, so it wouldn't be bad if you got started on it and so forth. Okay, so we'll have some time on that. I think I am going to let you work a little bit on the take-home quiz tomorrow in class 2. Okay? And I will give you a little hint about number 4 on the take-home quiz. So if you want to at least look at that one tonight, might be helpful. Okay? And then your assignment for Monday will be the take-home quiz. That will be handed in at the beginning of the period. And then we'll be getting ready for that other quiz and doing more packets next week. Get ready. All right. 4.8. And I'll put these 2 theorems up here. You got them? Okay. And right. And I had told everybody that